We're going to talk today about functions, a little bit about functions and graphs and domain and range a little bit. A function, your textbook tells us that a function from a set D to a set R, that would be domain and range, is a rule that assigns a unique element in R to each element in D. Now, that to me, that's a little confusing. We could just say that each element in D is paired with exactly one element in R. We remember that as a function. Each member of the domain is paired with exactly one member of the range, a unique element, exactly one. So then comes Mr. Euler, who invented a symbolic way to say that y is a function of x. So if our ordered pairs or our relation is a function, then we can say that y is a function of x, or y is equal to f of x. We've seen that before. That's called functional notation. So we see functions in calculus expressed a lot in functional notation. So let's look at this example. Write a formula that expresses the area of a circle as a function of its radius. The area as a function of this radius. So when we say that the area is a function of the radius, we're saying that the area depends on the radius. So the area is, we know, pi r squared. And if we want to write this in functional notation, instead of just calling it a or y, we could call it a of r. A as a function of r, written in functional notation. Use the formula to find the area of a circle of radius 2 inches. So when we're finding the area whose radius is 2, we're finding a of 2. Pi times 2 squared would be 4 pi. So a of 2 would be 4 pi, which would represent the area whose radius is 2. And what is the domain of this function? Well, let's see. The area represents our range. The radius represents our domain because the radius is its independent variable. So we can say that the radius of a circle is going to be at least 0. We know that the radius of a circle is not going to be negative. It could be nothing or it could be positive. So when we say that r is greater than or equal to 0, this is what we call expressing domain in set notation. We could also express domain in what's called interval notation. And when we say r is greater than or equal to 0 in interval notation, we would say that we've got from 0 to infinity. And we want to include 0, so we put brackets around the 0 to say we want to include. And we always want to put parentheses around the infinity symbol because we don't ever want to include infinity. Infinity is not an actual value, it's just an idea that we approach. So we don't want to ever include infinity. What's the difference between closed and open interval? So what we've got here is an interval. This domain is what we call an interval. And the interval would be like a range of numbers, a range of values. An interval is a range of values. So like we could say the interval from 5 to 10. The interval from 5 to 10 would be all the numbers from 5, in between 5 and 10, all the way to 10. And so the difference, so this, in this example, our interval is from 0 to infinity. Our interval from 0 to infinity. And we have a closed interval here. So this is considered a closed interval. We're not going to say infinity. Let's say 0 to 5. So when I want to say at least 0 and not more than 5, or all the numbers between 0 and 5, including 0 and 5, then I would call that a closed interval. But if I want to say all the numbers from 0 to 5, not including 5, so if we see an interval where we have parentheses around our interval, then we say that it is an open interval. So closed interval is when we include the endpoints. And open interval is when we do not include endpoints. Okay, so we're going to look at a few little functions and talk about their domain and range. The first function I see is y is equal to 1 over x. So we're supposed to be able to recognize y equals 1 over x as a rational function that does something like this. Let's see, if we go to our calculator, even though I'm thinking that you should be able to recognize this without our calculator, if I go to my calculator and I look at 1 over x, I look there and I see there. Okay, so we remember that we have an asymptote, a vertical asymptote on the y-axis. We also have a horizontal asymptote on the x-axis. So we would want to say that we cannot include 0 for x, and we do not want to include 0 for y. So our domain, in set notation, we would want to say x is not equal to 0. And for our range, we would want to say that y is not equal to 0. And if I want to express that in interval notation, so we're going to give domain and range in set and interval notation. In interval notation, we have to use 2 different intervals. So we want to be from negative infinity to 0. And we don't want to include 0 because we're not including 0. Remember, we do not want x to be equal to 0. And we need to use the union symbol. Union means we put them together. And from 0 to infinity. So we've got everything from negative infinity to 0. And everything from 0 to infinity, but not including 0. So that would also mean everything except 0. And it would be the same thing for the range. Okay, so we're going to look at y is equal to the square root of x. Y is equal to the square root of x. We recall. Looks like, I bet you know, looks like that. It's like it starts at the origin and it takes off up into the right. Curve up into the right. So we've got a graph that does like this, like that. And so for the domain, we would want to say that x has to be greater than or equal to 0, and y also has to be greater than or equal to 0. And we remember that that is true because the x is inside of the square root, and we know that the number inside of the square root will never be negative. So we want it to be at least 0. And we also know that the square root of something is always positive or 0. Okay, so in interval notation, we would want to go greater than or equal to 0 would want to be from 0 to infinity. And in this case, we want to include 0. So same thing for the range. Okay, and then the next one, y is equal to the square root of 4 minus x squared. Okay, so we're going to look at the graph just to help us this one time. Square root of 4 minus x squared. There we go. And so it looks like we've got this little half a circle. And I'm going to explain to you why I know it's a half a circle, because let's go over to the side. If I look at the equation x squared plus y squared equals 4, I recognize that as the equation of a circle whose radius is 2. Square root of 4 is 2. And if I were to solve for y, I would get this, and then I would take the square root of both sides, and I would get plus or minus the square root of 4 minus x squared. And the plus would be the positive values of y, and then minus would be the negative values of y. And so when I look at the graph, I see a circle whose radius is 2, but only the top half. So I know, so that's where that comes from. So I know where the domain is, everything in between negative 2 and 2. And do we want to include 2 and negative 2? Let's see. If I plug in 2, do I get a number that makes sense? 2 squared is 4, and 4 minus 4 is 0, and the square root of 0 is 0. So it does. So we do want to include negative 2 and 2. So we want to make it a closed interval and put our brackets around. That's interval notation. Sorry. There's our interval notation. So in set notation, we would want to use a compound inequality and say x has to be greater than or equal to negative 2 and less than or equal to 2. That would be an and compound inequality. And for the range, let's look back at the graph. We would maybe 0 to 2. 0 to 2. So y, let's make sure we call it y, greater than or equal to 0, less than or equal to 2. And my interval would be from 0 to 2, including both endpoints. So once again, it is a closed interval. And then the last one we want to look at is y is equal to x to the 2/3. So I remember that x to the 2/3 means the cube root of x squared. So we've got a cube root of x, and I remember that we can pretty much put anything inside of a cube root. We can put positive numbers, negative numbers, and 0 all inside of a cube root. So I'm expecting that the domain is going to be all real numbers. And so we remember we expressed that in set notation. We want to say x is an element of the real number set. Let's look at the graph just to make sure. Just because it's one of our first lessons. X to the 2/3 power 2 divided by 3. There we go. And I am right. This graph goes forever to the right, forever to the left. X can be any real number. But it also looks like y can't be negative. And I wonder why that is true. Why is it that y can't be negative? We're going to say greater than or equal to 0 because if I plug in a number for x, I'm going to take the cube root of it, and then I'm going to square it. And when I square a number, it will always be positive. So that is why. And so in interval notation, for all the real numbers, we want to say from negative infinity to infinity. And for greater than or equal to 0, we would want to say from 0 to infinity. And we do not want parentheses around that 0. We want brackets to include. Okay, the next thing I want to talk about just for a bit is the difference between an even function and an odd function. Some functions are neither even or odd, nor odd, but a function is even if f of x is equal to f of negative x. So in other words, if f of 2 is equal to f of negative 2, if the value of the function at 2 is the same as the value of the function at negative 2, and so on, then it becomes an even function. So for example, the easiest example I can give you is y is equal to x squared. Y is equal to x squared is an even function because f of 2 is 4, which is the same as f of negative 2. F of 1 is 1, which is the same as f of negative 1. Another example I can give you is y is equal to 4 over x squared plus 1. And I know that this function is also equal because if I plug in 2, or 1, let's start with 1. If I plug in 1 for x, and then I plug in negative 1 for x, I'm going to square it, so I'm going to get the same number in the denominator, no matter if I plug in 1 or negative 1, or 2 or negative 2, or so on. So these are two examples of even functions. Let's look at x squared real quick. I know what x squared looks like, and I know that it has symmetry. The symmetry here the symmetry is around the y-axis. So all even functions are symmetric about the y-axis. So we could make a note of that. Even if I look at 4, let's put in a fraction here, 4 over x squared plus 1, I see the symmetry over the y-axis, same on both sides. So we can make a note here that we have symmetry over the y-axis. Okay, now let's talk about odd functions. Make a little line here, separate it. Okay, let's talk about odd functions. An odd function is when f of negative x is equal to the opposite of f of x. So my example I can give you is y equals x cubed. Because for y equals x cubed, f of negative 1 is the opposite of f of 1. F of 1 is 1, but f of negative 1 is the opposite of that, negative 1. F of negative 2, f of negative 2 is negative 8. And that's the opposite of f of 2, which is 8. So let's look at the graph of x cubed. We know what that looks like, don't we? Yeah, we knew what that looked like. And so we see symmetry here. We don't have symmetry over a line. We have symmetry around a point. And the symmetry dealing with odd functions is the symmetry about the origin. So odd functions are symmetric over the origin. I can give you another example of an odd function, and that would be the sine function. Y is equal to the sine of x. Let's check that one out. Y is equal to the sine of x is an odd function, and notice the symmetry over the y-axis. F of pi over 2 is the opposite of f of negative pi over 2, is the opposite of f of pi over 2. I know that f of pi over 2 is 1. The f of negative pi over 2 is negative 1 in that case. So we've got another example of an odd function. So we have to know these definitions. We have to know very well that an even function is when f of x is equal to f of negative x. And we have to know that an odd function is when f of negative x is the opposite of f of x. And it's good to have examples under our belt also. So let's talk about compositions now. Suppose that some of the outputs of a function g can be used as inputs of a function f. We can link g and f to form a new function whose inputs are inputs of x, or inputs of g, whose outputs are the numbers f of g of x. This is the composition of g of x. So what's more important here is that we are able to do a composition. So let's look at an example. Suppose that f of x is equal to x squared, and g of x is equal to x minus 7. Let's find f of g of 2. So we're going to find f of g of 2. So first I'm going to start with g of 2. G of 2 is 2 minus 7, which is negative 5. And now we want f of 5. So f of 5, negative 5, f of negative 5 is negative 5 squared, which is 25. So f of g of 2 is 25. And now we're going to find f of g of x. So we're going to start with g of x. I want x minus 7. So I want f of x minus 7. F of x minus 7 is x minus 7 squared. So f of g of x is x minus 7 squared, or x squared minus 14x plus 49. Same thing. So we remember that the inner function goes in for the domain of the outer function. That's what we have here. The inner function, which is the function on the inside, becomes the domain of the outer function, the function on the outside. If you need help remembering compositions, I'll be more than happy to help you. Okay, so we have a couple more things to accomplish. I want to look at a couple of piecewise functions. Let's graph this piecewise function together. First, if x is less than 0, we're going to graph y is equal to negative x. So I know that less than means not including. So I'm going to draw an open circle at 0. And I'm going to draw the other points for y equals negative x and create that piece. So that would be the line y equals negative x, but only if x is less than 0. And then I want y equals x squared from 0 to 1. So from 0 to 1, I know that x squared, 1 squared would be 1. So I know it's going to do a little curve there, just from 0 to 1. It's kind of hard to tell, but that's okay. And if x is greater than 1, then y is equal to 1. So greater than 1, y is equal to 1, like that. So just reminding you that we have piecewise functions, and we should be able to graph each piece and what they look like and what they mean. So if you need help with that, just go ahead and come find me. And then we can go backwards. If I give you a piecewise function, can you write a function to match the graph? So let's see. We've got f of x is equal to, I see three pieces. So the first piece is if x is less than -1. Notice I see the open circle there. I see the open circle there. So I know I'm going to put just less than 1, and that is the constant function y equals 1. So f of x is equal to 1 if x is less than -1. And then I've got an in-between situation for this part. I've got an in-between situation. So I'm going to need to compound inequality there. So if x is greater than or equal to -1 and less than or equal to 4, then y is equal to the constant function y equals 3. Two constant pieces. And then lastly, I see that last piece looks like it's quadratic. So I wonder if we could come up with that piece if x is greater than 4. Let's see. That is the quadratic function y is equal to, let's see, it's got a vertex at 5, 0. So that means it's x minus 5 squared plus 0, I believe. Does that work? Let's check it out. I have a point at 4, 1. If I plug in 4, 1, do I get 1? Yes, I do. And I also have a point at 6, 1. If I plug in 6, 1, do I get a true sentence? Yes, I do. So I've got x minus 5 squared if x is greater than 4.